Okay, what are polyatomics? We'll find out today. Polyatomic ions is what we're talking about, and we're going to be dealing with how these polyatomic ions hook up with metals or other polyatomic ions to form compounds. And so let's talk about these guys here real quickly. So polyatomics is the first thing we're going to talk about. The prefix poly means many. Atomic means atom. So these are groups of atoms that are bonded together. And actually, these should be atoms. Let's change that to atoms. Groups of atoms bonded together that carry a charge. Groups of atoms that bonded together carry a charge. Now, we can identify polyatomic ions typically by their name or by having more than just one atom, a monatomic atom. We want more of them. And when we see those, we know we have a polyatomic on our hands. So usually in the name, they end with an "ate" or an "ite" suffix, although not always. There are some that do end with the IDE ending. So we'll have to be careful of those. Their charge is usually negative, although there is a positive polyatomic as well. Okay, and so what's going to happen is these guys are going to bond with metals, typically because metals have a positive charge, we remember. So you should have a golden sheet of nomenclature, which we handed out yesterday in class. And if you do not have one, there'll be some extras left today, so you can pick up another copy because you do need this. Or if you're watching this at home, I've linked through Classroom a golden sheet of nomenclature, so you'll all have one. And so this is a chart of the polyatomics. This is just taken off of that golden sheet of nomenclature. Again, something to notice, like we'll look like right down this left-hand list, is we do definitely have eights and ites and lots of eights and ites. We also have mostly negative charges. This is a -1, there's a -1, there's a -2, -2. Okay, mostly negative charges. There is the one exception. There's ammonium ion, which is NH4+. That means ammonium can bond with anybody else on this chart. Ammonium can also bond with just non-metals as well. Okay, so we have to watch those. Okay. And so what we're going to teach you how to do today is to name compounds using polyatomic ions and write formulas. So let's talk about how to name compounds first. So this very first compound here is KNO3. KNO3 we're going to name. Now we're going to ask a couple questions. So first, here's our metal. Our metal is potassium. And the question is potassium a transition metal? And hopefully for you the answer is no, it's not a transition metal. It's in the alkali metal group, group 1A. So we do not need a Roman numeral to name this guy. Then hopefully we can identify that we have this NO3. Now that is not a monatomic ion. We have one nitrogen bonded to 3 oxygens. So what we can do then is look up here on our golden sheet of nomenclature and find an NO3. And it's right up here at the top. There's NO3 1-. So this is going to be the nitrate ion. And so we're going to name this potassium nitrate with the ATE ending. Potassium nitrate. Common mistake students make is they'll call this potassium nitrogen oxide or potassium nitrogen oxygen. But please try to remember that you have a group of nonmetals bonded together. There's a good chance you have a polyatomic. Okay. On this next one, we're going to do the same thing. We're going to look at our metal. Our metal is calcium. We look to see if this is a transition metal, and calcium is in the alkali metal groups. It's not a transition metal, so no Roman numeral needed. And then we have oxygen and hydrogen bonded to it, OH bonded to it right there. Now, because we have more than one atom, this becomes a polyatomic. It is not calcium, oxygen, hydrogen, or calcium, oxygen, hydride, anything like that. This is a polyatomic, more than one at it. And so what we're going to do is we're going to look up here and we're going to look for an OH. Let's see if we can find an OH. Going down this row. Yep, there we have. We have an OH 1- right there, and its name is potassium, or excuse me, it's hydroxide. And we will tell you in the next segment why this has parentheses around it. And so for now, just naming them, we're not going to worry too much about our parentheses. Okay, so let's go down to our next segment here. All right, and then what we're going to do now is we are going to learn how to write formulas given polyatomic ions. So the first formula they gave us to write was sodium carbonate, And so what we're going to do is go ahead and write out the symbol, the charge for everybody, and then we're going to crisscross those charges just like we've been doing with regular alkali metals or transition metals. Okay, so for our metal, we're going to go ahead and look on the periodic table, and we get sodium. Sodium has a symbol of Na, and it has a charge of 1+. We know it has a charge of 1+. It's in the alkali metal group, and there we go. Everybody in the alkali metal group forms a 1+ charge for the most part. And then we have carbonate. Again, it has that ATE ending, which is indicating a polyatomic usually. So what we're going to do is we're going to go up here and look at our golden sheet of nomenclature, and we're going to find carbonate. See if we can find carbonate here. Yep, I see it right there. Carbonate is right here, carbonate, and there's its formula, CO3 2-. So we're going to come down here and write CO3 2-. Okay, so one thing that we have to remember about polyatomics is we will never change their formula. We're going to always, if there's a superscript on a polyatomic, for example, there's a 3 down here, that 3 always stays there for polyatomics. Okay, so what we're going to do again is we're going to crisscross charges. So we're going to take our 1 and we're going to bring it down behind the polyatomic. Now remember, we don't have to write 1, so we're not going to have to worry about that. And then we're going to take our 2 and we're going to crisscross it down just like this. So we're going to get a resulting formula of Na2, and then we're going to have CO3. Remember, we're going to crisscross those numbers down, and that's our final answer there, and we're good to go. Okay, remember, we don't need to write 1s. Okay, let's try another one. We have potassium phosphate. If you think you're up for the challenge, go ahead and pause the video and try it yourself, and then we'll come back and show you what we did. Okay, so potassium is a 1+ charge in the alkali metal groups. We've got to go up and find our phosphate. Let's see if we can find a phosphate up here. Phosphate is right here. Phosphate is PO4 3-. PO4 3-. Okay, so once again, we're going to do our crisscrossing of charges. Take the 1, bring it down. We don't need to write it. Take the 3, bring it down. We do need to write it. So we're going to get a resulting formula of K3PO4, just like that, and that would be potassium phosphate. Okay, now we come into our next problem, and there's an interesting thing that will happen here. We have magnesium hydroxide, and so let's go ahead and write down magnesium symbol, and it is a 2+ charge, as all alkaline earth metals are. And then the hydroxide polyatomic. This is one of those polyatomics that does have the IDE ending, but if you were to look at the periodic table, you're not going to find a hydroxide, so it is going to be on the golden sheet of nomenclature. There's hydroxide there, and it's OH1-. Okay, so we're going to put OH1-. Okay, now there is a rule that goes along with something like this, and the rule states this. If we're going to bring down a charge behind a polyatomic, a number behind a polyatomic, and the number, we'll say the number is greater than 1. So it's 2, 3, 4, whatever. We must put the polyatomic in parentheses. Everything is going to go in parentheses, and the number that we bring down is going to go on the outside of the parentheses. So here's what we mean by this. We have a 1 here on the hydroxide. We're going to bring it down. We do not need to write the 1. So this is going to become Mg. Now, we have a 2 here that we are going to bring down behind a polyatomic. We must put the entire polyatomic in parentheses. So we're going to put the OH in the parentheses and close our parentheses, and then the 2 is going to go on the outside of the parentheses just like that. Again, if we're bringing a number down greater than 1, we always have to put everything in the polyatomic in parentheses, okay? That's why we do have parentheses on some of those. Okay, let's kind of erase some of this off. Hopefully you wrote that down. If you didn't, you can just rewind, and there we go, chromium. Okay, so here's another one. If you would like to try this yourself, you're more than welcome to. We have chromium Roman numeral 3 nitrate, and go ahead and pause and try it yourself, or you can just watch along, and here we go. So chromium is Cr. Chromium is a transition metal. That's where we have our Roman numeral coming in. And so that Roman numeral, remember, tells us our charge of a transition metal. So this is a 3+, plus the nitrate ion. Nitrate, once again, with that ATE ending, it's a polyatomic. So this is going to be NO3, 1-. We're going to crisscross those charges. This 1 is going to go down there, so we don't have to write it. So we're going to have Cr1. No, don't need to write it. We are going to bring a number behind a polyatomic, so we're going to put the whole polyatomic in parentheses, NO3 in parentheses, and then the number is going to go on the outside, the number 3. Okay, let's show you one more here that's really, really important that we need to deal with. Okay, so this one will be the last one that we take a look at, and so we have calcium carbonate. So calcium has a symbol of Ca, which is a 2+ charge, and carbonate, we look up on our golden sheet of nomenclature, has a formula of CO3 with a 2- charge. Okay, so once again, same rules apply, crisscross. We're taking a 2, we're bringing it down, we're taking a 2 and bringing it down. So I'm going to write this guy out, how we would do it, and then we're going to talk about something neat that happens. So we have calcium, and we brought a 2 down from the carbonate, so we have 2. Put everybody in parentheses, put the entire polyatomic in parentheses, and then the 2 from the calcium is going to go on the outside of the parentheses. Okay, like that. Now, we are not finished. If you remember in writing just regular ionic compounds and ionic compounds with transition metals, we always need to reduce. Now, in this case, we can reduce. Now, one of the things that we will not reduce is we will not reduce anything to do with the polyatomic. That formula needs to stay the same. But what we will reduce is we will reduce our number that is behind the calcium here and outside the parentheses there. So in this case, we have a 2 and a 2, which are divisible by 2. So that reduces down to CaCO3. Now that is essentially saying we're taking a 1 and bringing it down behind the calcium or the carbonate. And so we no longer need parentheses if it's a 1 and a 1. So this would be our correct answer. Again, if we can reduce outside the parentheses only, we do reduce. We never reduce inside the parentheses on the polyatomics charge, or excuse me, the polyatomics formula. And that's how we deal with polyatomics and writing formulas and naming formulas. And there'll be some practice that goes along with this.